Dear ladies and gentlemen, I'm sure if it works or not. Maybe it actually doesn't work. Is it working? No, maybe it's not working. Oh yeah, it works finally. It unfroze. Oh, dear love peace, I'm very happy to see you here. So you are the main guest here, and it means that we maybe can start. And fortunately today I have some problems with internet, that's why the video is very bad. I mean, I don't see that I'm moving actually, but can you hear me at least without distortions? Yeah, I don't know like what to do with this. Maybe there is a problem with internet. Yeah, I also don't see any video. Unfortunately, I'm very new to stream. What can I do with camera? Okay, I can maybe switch camera. I don't know really. Yeah, I really don't know what to do about it. I'm not prepared to this thing, like that camera can be frozen. Okay, I will just try to turn on my mobile internet and reconnect from mobile internet. I'm sure that it's a good idea. But let's see. Okay, is it better now? Maybe no. Okay, maybe it's better and maybe I'm at least not fully frozen. Okay, dear love peace, is it better now? Sorry. Okay, it's better. But I don't know why there are actually, I don't see comments in the chat. I see them only on my chat on the screen. Okay. Okay, let's try like this, and maybe it can not be a problem, because anyway, if you hear me well, then it's the most important thing. And I can't right now fix the video because that's Bulgarian internet. Okay, if I do like this, maybe now you can see some screen of my very intensive preparation to the stream. Yeah, there is actually a delay also in video. Okay, I will just, I know what to do. I know what to do. I will do like this, and then I do like this, and then I do like this. Remove. Okay, now you might not complain that you don't see me freezing, because you will just not see me, and you will see just something that I show you. And if someone watches, maybe you can tell me if you hear me well, because if you hear me well, that's the most important thing. Or at least if you don't say that you don't hear me, it means that you hear me. So I can maybe start talking. Okay, so like today there was idea to tell something about polarons, and I was like working with polarons for like 3 months or approximately maybe 4 months totally. And it's a really complicated topic because as far as I understand, there is not a very clear understanding right now how polarons work. However, people know about them for maybe 90 or 80 years. First works about polarons appeared in 1940s by Landau and Pekar. Yeah, like here you can see their articles. It's not really important to understand what has been discovered there, but that's like a proof that some first discoveries were done in 1940s and then 1950s. And yeah, like the first article, which is often cited as the first article, was written by Landau in 1933. Then there was some steps forward in 1940s. Then not so much was done, but still something was done in 1950s, 1960s. And after there was a big step forward in different directions in theory of polarons in maybe 1990s and later. So let's maybe start with what is polaron in general. And yeah, maybe I don't have a beautiful illustration of it. But okay, the idea is actually very simple, and maybe it's a good idea to show you the original article by Landau with some of my comments, which I wasn't looking at for a long time. But the first article was just of 1 page long, and okay, the main idea here should be that if we put an electron in material, then it should attract some positive ions, and that's how it can behave in a special way. I actually didn't read much this first article, but I know that that's how it looks like. And it also doesn't give much predictions. It even asks more questions than gives answers. But okay, just I wanted to tell you that that's the main concept. And I was trying several times to connect theory of condensed matter, where we are told that electrons are described by, I don't know, tight-binding models or by Green's functions, and lattice is described by phonons, and then there is Green's function for phonons, and we know how to calculate like heat capacity of metals because of phonons. So I wanted to connect that theory with the theory that, for example, Landau wrote, or theory from the book that will be main book for this stream, Alexandrov and Mott book, and like introduction to the very short. I will give you a very short introduction to this book. So Mott is the Nobel laureate who is famous for his works in condensed matter. He discovered Mott insulators, Mott transition, and maybe many other things which I don't really know. Hubbard Mott insulator is also. I'm just telling you something that I heard several times of, and that's what is really famous. And Alexandrov is a Russian scientist who wrote very complicated theoretical papers, and he is most famous because he pioneered work of Polarons. Maybe I can actually give you even a preview of what happens in the theories. So yeah, something like this. And also there are some strange diagrams which I didn't write. So idea of what I'm telling you right now is to give you just an impression what Alexandrov liked to do. So I was actually trying to find several times how did he manage to do this at all. I mean, not at least trying, why he was trying to do this at all, because it's very unclear how he got like this understanding of this strange formalism. I have no idea what happens here actually, and I still can't trace where he took this formalism from, because that's not the formalism from Abrikosov, Gorkov, Zelashinsky, which you might remember from the previous stream. By the way, yeah, I just thought that, yeah, okay, I hope that there is sound. If there is no sound, then please write in the chat. I will try to fix it as soon as possible. But okay, introduction to this book is that one author is Nobel laureate, another author is not a Nobel laureate, but he's famous for his strange works about polarons. He was doing very special transformations of operators, and then he was coming to some strange conclusions, which for me is very hard to analyze for their physical sense. And this book is approximately of this style, but we're not going to, of course, discuss these strange methods and statements. We will just look at the first part of this book. In the first part, actually, I even have selected them here in this application which I'm using, which is a focus structure tool. So here I just selected the first chapter of the Alexandrov and Mott's book, and that's our plan for today. I also have selected a long time ago some formulas which might be useful even now for us. So for reference, they better to be here. Maybe we will return to them, maybe we will not return. Oh, okay, but I know what we will definitely return to. And that's the summary of what I plan to tell you today. Okay, not everything is just one model, and I'm planning to speak about 3 models. Actually, they're summarized here in this nice substructure. So there is a famous Landau-Pekar model, which is also shown here, which is a continuum model. Then there is already quantized model, Fröhlich model. Then there is a third one, which is called Holstein model. And already at this stage, a lot of questions can appear, and I still don't know answers on these questions. Like the obvious question is that how we can derive these models from some one general model, and I don't know, because okay, I know the answer, I can show you some complicated formulas, but they are not really answering this question. So that's like, if you ask this question, you can show this derivation, but it's a very unclear derivation. So to be honest, it's better to claim that this question is just unanswered. Another unanswered question is that how these models are connected one to another, and sometimes it's easy to answer this question. I mean, partially, but sometimes it's hard, because like one can say that we can get the Fröhlich second one model from Landau's model by quantization of Landau's model. And if you ask this question again, because it's still not clear how to quantize this strange model, which I haven't even introduced, but I will do it after I finish this introduction. So if you ask someone how to quantize this model, and if this person knows something about polarons, maybe he would answer that look at the original Fröhlich work of 1954 year, where he did something, where it's written that he did exactly this, he did this quantization, but it's still also very, very not clear. By the way, I maybe even have this this article. Okay, maybe I have it in another note, another version of this note, because I have two parts of my note, and that's the first part, and I'm not sure. Oh yeah. It maybe that's maybe the article, Electrons in Lattice Fields by Fröhlich. And actually, yeah, there are a lot of people who were contributing to the field of polarons, so maybe this stream will give a good introduction of what's going on there. But there are so many authors from the past who tried to develop this theory. And I mean, when I speak about, say, past, I mean 1950s, 1960s, and some Nobel laureates like Landau. Feynman is also famous. I mean, not so famous, but if you deal with polarons, often people cite his work where he used path integral approach for polarons. Now, like the Fröhlich is a very famous scientist who like is famous for the Fröhlich interaction term, which couples electrons and lattice, and all this theory. Like even if we don't have polarons, all theory of electron phonon interaction is basically called the Fröhlich theory. Okay, so they were trying to. They were trying to develop theory of polarons because they really wanted to have some physical predictions, and it was like a long process. And right now in 2026, after spending like 3 months, I can't tell you what are exactly physical predictions, like which plots are explained. Yeah, by the way, I can maybe take an advantage of this application and just open something. Uh, uh, so yeah, I'm just a little bit distorted to Telegram. So yeah, why this application is, by the way, useful is because, for example, if I want to open some experimental paper, yeah, I can do like this, and then regret that I'm doing like this because it's not really finished. So if this table of contents is too big, then it doesn't really want to load it. But these are the experimental papers which I tried to open some time ago. And right now, yeah, at least there is a synchronization. Right now I'm trying to restore some information about what's really obtained from experiments. And yeah, I know some experiments like ARPES, which is the famous experiment. So there are some peaks that correspond to optical absorption, and there is some theory that follows from this fundamental theory that calculates, for example, the optical conductivity. So if we shine light on some special material, then sometimes more electrons go and travel, and it's claimed that that's because of polarons. Sometimes it's not really clear if it's because of polarons or because some other phenomena. And at this point, a lot of discussion happens in articles where authors try to argue that that's exactly because of polarons. Maybe I can actually find in this note, maybe this paper, let's see. Yeah, so maybe that's that's the paper which I have even discussed with the author of this paper, with Dragan Mikhailovich. So they claim somewhere here in the introduction that they have discovered polarons, and they use some special method here, which I actually forgot how it's called, but just I wanted to be fair with you and tell you what really theory of polarons is giving us. So they were saying, okay, I forgot how this method is called, unfortunately, but maybe right now I will remind myself this. Yeah, it's called X-ray pair distribution function measurements. So I'm not expert in this topic. I had just several discussions of this thing, but I can just tell you what I remember, that pair distribution function is this one, or this one, pair distribution function. So there is actually a Wikipedia talk article about this thing, but it's somehow connected with the correlations between some electrons as a function of distance. So that's the plot of this. It's called, yeah, I remember, it's called PDF, like the format that we're using here, PDF files, but it's a pair distribution function. And it's measured like this, that on x-axis you have a distance, on y-axis you have some this PDF, and this PDF tells us how some points in space are correlated. You can ask me many questions, what does it really means, and I don't know, but what I do know is that it looks like a chaos. Something is more correlated, something is less correlated, but these people really know what they're doing. I'm sure that this article makes sense, and it's not the only article that uses PDF method. And they use it for some special material, tantalum disulfide, which is also very famous in my institute. So the outcome of all of this big theory, which is like 90 years old, like, because yeah, we can calculate. Landau first, as it claimed, introduced this idea in 1933, and now it's 2026, so it's even more than 90-year-old theory. So in 2023, this theory gave the following prediction in this strange PDF method. It gave this peak, and this peak is impossible to get from other methods. And the second method, which is also a competitor to Polaronic theory, I mean, not method, but theory, that is competitor to explain some experiments, is theory of charge density wave. And this peak can't be explained using charge density wave theory. That's what an author of this paper told me. So how to get out of this window? I didn't write, sorry. I need to close, then do like this. Okay. So yeah, that's little overview of what theory of polaron gives us. It gives a prediction of peak on, for example, how is it called? Pair distribution function measurements. Is it useful or not? It's not a question that you can ask me. It's a question you can ask authors of this paper, because it looks very, very useless. But it's not the only one prediction of polarons. And maybe that's the value of this article, is that we know that this material should be explained by theory of polarons, and using theory of polarons, maybe we can predict some other properties. And by the way, that's approximately my PhD task, to develop some new advanced polaronic model for some physical effect. Okay, so like that's introduction, that there are some experiments that give some peak. There is an experiment that, yeah, which give another peak, another measurement. And that's the motivation to study this theory, because well, it's not clear how this theory is used in that experimental articles, but if you think about polarons, that this is the most well-known theory, and it's impossible to claim that you know polarons if you haven't mastered these just three models. And today I will not maybe manage to really explain everything. It will be again like overview of what happens there, and I think that that's even better than if I was explaining in detail what's going on in this model, because it would be too much information, too many complicated things. So it's even more advantageous to say shortly what is the main idea and what are the main conclusions. Okay, and that's our plan for today, the three models and then discussion of them, and maybe also some comments about some connections with the well-known theory of condensed matter. However, these questions are not answered for me, and also they are not answered in literature. So if you try to read literature about polarons, one article uses one method and they cite something, but a lot of things are stopped only on the level of claims that something should work somehow, but without any comments, without any real connections between what they do and what happens in other articles. And that's why I also don't know how many things are connected, but I know approximately how this model works. Okay, so let's start with the most famous and the old model. It's not really clear how many there are physical predictions from exactly this model, because book of Alexandrov and Mott writes that because of some special reasons this is an unphysical model, but not all authors, not all scientists agree with it. Some people with whom I discussed this said that no, actually that's a good model, and it's used also. And the second Fröhlich model is a particular case of this model, so it's not really clear is it useful or useless. It's also not really clear how to get some experimental predictions of this type, for example, from this model. But I can bet that someone really knows it, and maybe not the only one person in the world, but a lot of people who specialize in polarons should know this. So before I start telling you the derivation, which is a okay. Before I start telling you the derivation, maybe I should just give an overview of the result, because that's the best approach not to get lost in everything. So the statement of the problem. So the statement of the problem is that we have electron. Electron travels through polar crystal. There are no other electrons around this one selected electron. So you will hear nothing here about Fermi C, this Pauli principle. No, this thing wasn't maybe ever discovered when this model appeared. And that's why it's really hard to understand where it can be applicable. Some people say that this model is applicable for semiconductors, because in semiconductors there is a valence band, conduction band, and conduction band is approximately empty. So approximately one electron is really conducting and other electrons are sitting on atoms, and they just contribute to polarization around this one selected electron. I didn't check that this model really works for semiconductors. That's what I stopped on when I was thinking about it. And also, maybe we call them ionic crystals. What is an ionic crystal is not really described here. Of course, we can look at formulas and define ionic crystals as the crystals for which this formula is applicable. But it's of course not a professional definition. So maybe the ionic crystal is a crystal where there is some absence of electron or existence of extra electrons, such that there is extra polarization if some external field is applied. But okay, for some special crystal, there is this one selected electron that travels through, and well, we are asked to get some properties of this electron. Then it's really not clear how to get some properties of the whole material, and like of course we measure properties not of one electron but of whole material. But it's also not explained in this book. It's also not explained in Abrikosov-Garkov-Dzelashinsky, for example, Bible of Condensed Matter. And actually, I even don't know any book of condensed matter which is not focused on polarons that describes this. But yeah, if you really want, I can just tell you that there is this book, Fröhlich Polarons by De Versy, and as far as I remember, he has a lot of derivations here for optical conductivity, so on, so we can easily open it. Boom. That's why actually I was creating this application, that if I want to open something, I just open it, and I don't need to scroll, I don't need to open other PDFs. And show you some type of derivation. So some derivation like this happens, and then because of correlation functions, somehow we get optical conductivity. Yeah, this thing that I was introducing before. It's not actually the thing, the article that I was reading. I just know that it's done there. I was reading another article, which is better not to even try to find because I will be too much distracted. Maybe here. Okay, it's better really not to do this thing. But okay, if you want to get some physical consequences, I'm not sure that that model can give you them, but you can try read article by De Versy, and yeah, yeah, De Versy is from Belgium. Yeah. 1 second. Okay. So, yeah, De Versy is famous for polarons and for maybe something else in condensed matter. But in polarons, he's a rather famous person. So, let's try to, at least for me, let me try to state the main idea, the main conclusion out of this model, because there are not so obvious transformations here, and later we will look at the transformations. So the first conclusion that if we put electron in a material which creates polarization around it, the first conclusion is that this electron becomes localized. That's why some polarons are also drawn artistically as bubbles, and maybe on this preview of the stream they were shown as bubbles, because the first prediction which was ever made for polarons is that they have some radius. So the prediction is like this, that this radius equal to constant times this value, Bohr's radius, but for polarons, and to find the Bohr's radius, but for polarons, you need to have this constant here, which is a very, very famous constant for theory of polarons. It used the electric function on different frequencies of external field that is applied. And it's not. I actually tried several times to find these values for some materials to get some explicit value of the radius or something else, because a lot of formulas use this kappa value. And I didn't succeed. I saw one table that states them, but okay, it's still very not easy to get these values and be assured in these values to say that exactly this is the radius of polaron for exactly this material. But okay, maybe I'll try once later. But the main thing is that we can shine light on material, somehow measure different dielectric functions, then calculate kappa, and then predict that electron has the following radius. And that's one out of three predictions. The second out of three predictions is that electron is not really moving, at least in what's written here in the whole first 3 pages, okay, maybe even 4 pages. We do not assume that electron is moving, and later if it moves, then there is the third prediction, there will be the third prediction. But if it's not moving for some reason, maybe because of absence of external field, then it has ground state energy of this formula, which uses the same constant RAB, like Bohr's radius. Okay, and of course this I should say that this approximate value. Oh yeah, by the way, by radius I meant that the wave function looks like this, that it decays exponentially. It's not really a ball, it's an exponential decay with this parameter in the exponent, and a is the normalization constant, which doesn't matter right now which value it has. So that's this energy is used to, I mean, sometimes people speak about this energy in a way when they say that electron creates a well around itself because of itself, because here in this whole model, here we claim that this polarization is because of field of electron. And that's how there is a potential well because of the electron itself, and it becomes localized. That this is what we mean by localized, that the wave function is decaying, it's not a traveling Bloch wave, and it sits in this potential well on this constant energy. Okay, you can ask a lot of questions. I can ask also a lot of questions. What is really meant by this? Is it really confirmed somehow by experiments? But as far as I understand, actually, yes. Like the main thing that's like a useful result, because if we shine light on some special material, I guess on semiconductor, then if you shine a light of particular frequency, which equals to the difference of frequency from the conduction band to this ground state energy, then electrons will be excited. And if you shine different frequency, then it will be not excited. So maybe exactly this formula was even measured, because definitely there were such experiments, which I'm describing right now. But I haven't reached this point of understanding which exactly experiment can be. But yeah, that sounds like a useful result. We just need to find the proper frequency, and if we see peak, then we see that, yeah, great, we can describe by this model our material. But if we don't see peak, then there are 30 or 50 different questions which can arise and which can explain why this model is not applicable. So it's some kind of sketchy model, but that's science. It's not fully finished part of condensed matter. It's still the development is still undergoing here, and especially in theoretical part, because from theoretical side, that's a bad theory from theoretical side, because we want to plug some particular properties of material to this model and get some experimental predictions. That's the best theory which we can have for condensed matter. And as you see, it's impossible to plug some particular properties. Maybe the only point where we can do it is here, but it's not really clear if we can apply this model or not for some particular material. And even if we can, it's not really clear. I don't know any like how's it called, not textbook, handbook of these constants for material. At least I haven't seen it, but I have tried several times to find it. So everything here is not really well developed, even though nearly 90 years has passed since this idea appears. And it's not only one direction. There is also mathematical, physical, like view of mathematical physics on this model, and there are also a lot of unanswered questions there. But that's how it works. These are two predictions that electron is localized and it has this energy. And the third out of three prediction is that if electron is finally moving, okay, there are some complicated formulas which I will comment later, but if it's moving, then there is a change of mass of electron. And okay, I don't know how to comment this formula which I took from this book. I forgot about this formula. Maybe it's a change of energy, but let's not look at it. So the change of mass is like this. And when you look at this formula, you might ask me, we all know that like if you calculate electron phonon interaction, then there is also like contribution of phonons, and is it the same contribution or not? Okay, maybe I can open you a book of condensed matter where I have this thing. Usually, next time I would open my application which I want to promote, but right now I'm not sure that it will work or not because I'm developing it right now. Today cursor lied to me like 30 times that it fixed the problem, and then he didn't fix. But I just wanted to show you some basics also of polarons, which I also tried to connect with the theory that I was showing you, like here, this professional theory of polarons and theory of polarons in scope of just condensed matter, where I wanted to extract K ideas and not write some exotic ideas. It's not done, of course, but I just wanted to show you that in scope of condensed matter, we also say that there is a change of mass. And this change of mass, of course, I know that it's not English here, but it doesn't matter what's written here. Change of mass appears because of self-energy. And yeah, maybe I should have made a stream about formalism of condensed matter to explain more something about self-energy. But the general picture is that we have an electron that travels through matter, and maybe always we can describe it by Green's function, and Green's function is a bare Green's function plus this self-energy. So to get the effective mass, you need to calculate self-energy, and that's what is done here. That's formula for self-energy. We plug some Green's function, then some complicated mathematics, which is not interesting at all, happens, and then this formula for the self-energy gives us some mass enhancement. Unfortunately, I don't have another theory, but I mean, another theory is in the book, but not in my note. But there is this standard approach for mass enhancement in scope of condensed matter, and it goes from this idea of calculation of self-energy. And you might ask, is it the same as, oh, sorry, I need to click here, as this mass enhancement? And unfortunately, I don't know. However, I asked this question maybe half a year ago. And that's a very peculiar and strange mass enhancement. I really don't know. Or maybe even not enhancement. It's not really clear if m star is bigger than bare mass of electron. But in scope of this theory, nothing else exists. We have just this change of mass, and we need to believe it or give some reason why this model is wrong. But it's easier to believe this model than to give a reason why is it wrong. But idea is that, yeah, like if there is some reason for electron to move, if it has a speed v, then its energy is written like this, that we have this deformational energy. I mean, maybe not energy of electron, but energy of the whole system. It's a deformation energy, some constant which I forgot. That's reality, I don't remember everything. And the kinetic energy of electron with some effective mass. And the effective mass, again, is calculated through fundamental constants. Maybe omega is the frequency of external field that is applied. I haven't ever actually understood really well this formula. I always believed this formula. But it's not the really theory that I was focused on. There are more useful theory. It's just my general education that I try to understand deeply this exactly theory. So I assume that omega is an external frequency of an applied field, and later I will comment why this term appeared. So this alpha that stays here, it's called a Fröhlich constant, and so that's the formula for mass enhancement. It has just a constant times the bare mass, and this constant has this kappa, which is the famous kappa that I was introducing before, the difference of the electric functions. And this is the main idea of this model. Maybe okay, Yannick, bye bye. It was very nice to see you here. Yeah, I'll write this. 1 second, I'm a little bit distracted, but it's important to say thank you for my dear viewers. I really am happy that he came. Okay. Yeah, okay, so let's continue. If you have some questions, of course, ask them and I'll try to answer. But the general philosophy of this approach to science and this stream is that we are not trying to come to some final understanding of some models, because it's usually impossible, and there is also not so much sense in it, because some things are left only as open questions, and it's normal. That's how we naturally do, like how we naturally think about topics. So like other people would say, like, I know and I understand well thing that I'm telling you about, and they have mastered for 10 years this topic, then you will see maybe that that's not the case. You will be disappointed. And here you will not be disappointed, because I am fairly telling you that no, I understand this model only to some extent, but the advantage is that it's really very, very hard to understand what's written here better than how I understood it. You would need to read other papers, and usually no one is doing it. It's way better to hear someone who was thinking several months about the topic than to try to understand yourself, because you would need several months. So maybe I need to say something about the derivation here, and the derivation is somehow complicated, but maybe I will just start with the beginning formulas and skip, of course, mathematics. So there is this formula which is actually very complicated. It looks simple. I mean, one can say that it looks simple, but there are very deep ideas here, and so it's not an idea. I can't explain this formula in this stream, because I can speak like at least 20 minutes about only this formula. So maybe I will not comment much, I will just state correct statements. So the correct statement is that we combine here quantum mechanics and electrodynamics. It's also very not obvious why this works this way, but that's what Landau and Pekar wrote according to Alexandrov and Mott. But maybe Pekar was more responsible for this formula. But okay, the idea is that we say that this is the typical kinetic term, this is the typical potential term. Psi is a wave function of electron. Why we integrate over dr is because, well, that's like energy. Energy is a scalar, and wave function is like there is a quantum mechanical formalism that tells us that that's exactly the energy of electron, free electron. So we should not doubt this term. But now there is this term which has many features. One of the feature is that there is a minus here. I right now forgot why there is a minus here. Maybe because of this reason that but potential is dipolar moment times the field, and this is the field which was created by electron, and that's the dipolar moment of all the lattice, because that's a polarization of lattice, and it's sum, and total polarization is sum of all dipolar moments, and that's why we have this formula basically. Now we say that the field which was created by electron is written according to Maxwell's law, and in Maxwell's law we had the gradient of potential, and potential, electrostatic potential, is calculated like if we had a charge, it's like a field of the electron. If it's not clear, then write me in the chat. There is here empty chat which tells me that or there are 0 viewers or everything is clear. Yeah. So it makes us, actually it's better to write here somewhere the original Maxwell equation, which is assumed here. But okay. By the way, what's with the internet? I'm connected to my phone internet. Okay. So there are many things that are not very obvious here. Like, for example, if this is a field inside of material, why don't we have an epsilon, the electric constant of this material? And why at all we are looking at one electron and then saying that it's like smart if we like claim that there is the Copenhagen's principle that electron is only at one place. But that's how we can see like this connection of quantum mechanics and electrodynamics, that like we need to think that field is created from all of the positions of electron instantaneously. That's why we just integrate over the position, and this is the density of electron, like squared, absolute value squared of a wave function, and this is basically the potential, but we just integrate it because wave function is spread through a lot of coordinates. And that's how we have this field D. Okay, that's the initial formula. Then right now I will skip the mathematics because yeah, if I was speaking about mathematics, I would spend like 20 minutes. And the idea is that if we had just this model, that's already enough to deduce approximate value of the energy. So the idea is that we need to minimize this energy, and fun exercise for I don't know who, but it's really a fun exercise to go to a community of people who are doing mathematics, give them just this model and ask them to find the energy. It's actually a nice exercise to ask ChatGPT not to tell anything about polarons and ask about finding minimal energy, and compare what will they do with what is done here. And here the variational approach is used, which works approximately. But if I didn't know this approach, I would not solve that exercise. That looks very not typical exercise, like not a typical exercise. Okay, and by minimization we get the wave function, and then after we plug the wave function we get the ground state energy. There is an activation energy of a polaron, and there are different other wave functions that can be plugged, but okay, I haven't been using this theory. I actually forgot about this activation energy, and other trials wave functions are, they look very straightforward. I'm not haven't ever been motivated to redo this mathematics to get more precise results. Let's just believe Pekar, who, as far as written here, claimed that for this different wave function you get more exact value of energy. Okay, nothing should be wrong about it. Okay, now there is the extension which I should explain somehow, and the extension is this model. Yeah, maybe it's a good idea to put some key formulas here. And the idea is that if there is an external force, then lattice polarization has a dynamics. There is even an equation for this lattice polarization. And maybe it's better not to even comment this, because it looks very not obvious and not so much is commented about it. And when I was working with polarons, I haven't ever discussed this formula with anyone. So no, I don't right now understand immediately why it is so, but that's what we are told, that right now we have external force and polarization is not just thing that is written here. Okay, I didn't comment this thing, which is a very actually important formula, and that's the origin of kappa, but I also haven't rewritten this theory after thinking first time about it. I mean, not first time, but several times. I had discussions of this, and I didn't rewrite this part. But before it was like this, now it is like this. There is this term that is added because of external force. Now we have time dependence and we have a frequency. So that's like a wave equation with external force. Let's just believe it. And then we plug the same polarization, I guess, to the previous functional, or yeah, maybe we have the, not we plug, but we have a different functional here. Yeah. sorry for a little distraction. So now we have a more complicated functional where there is the term which corresponds to dynamics of polarization. It's really not obvious how to get the result which I claimed from this theory. Yeah, maybe the right way is to just follow the words here, which I haven't ever followed, but like it's obvious that it will be true that if you plug this, I mean, it's not obvious, but there is no reason to doubt that this result is true, that if you plug different ansatz, then you can re-express this equation in this form, where you have already a v, the speed of electron, and something before, which is ms. Yeah, as you see here in my comments, I was ever very lazy to derive it. There's also like a sign that this is a useless theory. We don't need really to be stuck on this derivation. It's like just for personal pleasure, one can derive it. Somehow it works, and then if you just plug the polarization, I mean the field, electric field in material as a function of wave function to the equation for effective mass, you get the effective mass, and you know the wave function of electron. That's why you get the expression for the wave function. That's how it works. And then there is a complicated and not very explained theory about limits of applicability of this model. And here it's claimed that there are no solids where this model is applicable. The problem with this derivation is that that's a really unclear derivation. So I don't really know what to comment about this thing. I was thinking at least 5 times in my life about this reasoning why this model is not applicable. And it's written actually here, and okay, it's actually a deeper understanding which is not connected at all to many things that are explained before. Actually, it's a different idea about some quantizations, about comparison of lattice constants with lattice constants, something. So two conditions should be satisfied, and they're not satisfied. That's why this model is not applicable. That's a bad explanation here, and I don't have a good explanation, so let's just skip it. But if you are really interested, you can read what's written here with green my comments and red my questions, and maybe it will give you some understanding, but no one maybe will be ever interested in this. Maybe one day I will find another place where it's written better than in Alexandrov and Mott's book. So I will then return to this question, but currently I haven't ever seen this derivation in these reasonings of the model that it's not applicable in any other place except this one in Alexandrov and Mott's book. That's why I skipped this thing. I understood it to some extent. I mean, I discussed it several times, but nothing much happened from this discussion. Still, we don't understand for which materials this model is applicable or not. So sounds like a bad idea to be very stuck on why is it applicable or not. And there are no actually also references here, so who knows where they took these reasonings. Okay, we have covered the first point out of 3. The second point is the Fröhlich large polaron model. So right now we have these are the K formulas. And by the way, advantage of this application is that right now I just need to little scroll and see the K formulas already extracted. I don't need to scroll, I scroll a lot to open other files. That's why it's focus structure tool, because I'm very focused. And here there is the collection of main formulas for Fröhlich model, and on the right side you see a derivation. And it's also actually a complicated derivation which uses a perturbation theory, as you can see here. Let's again start with key formulas, not to get lost in all the information. So we are proposed to deal with this model, which is derived also, of course, but right now let's just look at this model. And the Hamiltonian, as I announced before, consists of electrons and phonons. So the energy is written like this. This is the term that corresponds to phonons. We have d operators that create them, and as you can see, it's a purely different word where you have a second quantization. You have these operators at all. Before you didn't have them, and I forgot if they are in Holstein model that I'm going to cover the third one, but we'll see soon. And there is an operator for electron. It's a kinetic term. I actually don't remember why we don't have second quantize operators for electron field, but we'll look later on it. I can show you later some more advanced formula of the Fröhlich model. There is an idea of the derivation which is sketched here, and I'm going to speak about it very soon. But the result of this derivation is presented here, that we have purely electronic term, purely phononic term, and the term that corresponds to interaction of electrons and phonons. This is D. D corresponds to electrons. V okay, let's just open the something. No, we need to open. I will tell you what do we need to open. We need to open this thing. See how I very fast got the required section without a lot of scrolling. So advanced version of the Fröhlich model is like this, that we have quantized electronic field, quantized phonon field, and an interaction that is famously written like this, that we have C dagger, C and D plus Hermitian conjugate term. We have two operators of electrons and one operator of phonon. That's a typical form of the Fröhlich Hamiltonian. And here, like everything what is left is that this V should effectively have these C dagger C operators. Of course, we don't see them, it's rather constant here. Okay, but that's like how Alexandrov and Mott wrote it, so I'm a little bit lost again, but it's impossible not to be lost because we have two terms which should be equivalent, and obviously it's not clear if they're equivalent or not. But Okay, let's go back to the thing that we really need, and we need this one, Fröhlich large polaron. But the conclusion is that we derive this Hamiltonian from electrons and phonons. And then we work with this, again, Hamiltonian to get the same thing, the mass enhancement. And right now you can see that there is a different prediction. It's very, very, very not connected to the previous prediction. Before there was alpha to the power of 4, now it's alpha just divided by 6, and also plus 1 is here. Of course, it's very hard to understand what is the limit of applicability of the first model of this model. At which point this model is applicable, at which point the previous model is applicable. And of course, because this is not written explicitly, I also better skip this important discussion. But what I wanted to tell you is the idea of how do we get here, and also the idea of how to get the similar result but for different value of alpha, because here the perturbation approach works for only little alphas, but if alpha is in this range, then there is a special different transformation, which I will just shortly discuss. Unfortunately, there are no questions in the chat, which means that exactly zero viewers enjoy it and understand it. But the good thing is that no one is here who do not understand what I'm telling. Okay, but the real value of this model is maybe the same as the previous model. We have the same type of predictions, but for where is it actually? But for a different model. So the first prediction is the ground state energy and the change of mass because of movement of polarons. Yeah, that's not important things. So nothing really useful is obtained here, but it's actually very hard to obtain even these results of a new formula for mass enhancement. And this is this formula. But if you think about it more, it's actually a good thing to spend like free time on, except that it will not help you anyhow in your research. But it's a good philosophical question to think, how does it happen that that model give you that prediction, this model gives you this prediction, because the predictions are different, so you need to explicitly say in which case this prediction works and in which case the previous prediction works. Let's just leave it as a good philosophical question to think about in free time. Right now I just want to sketch the main ideas of derivation. So idea is that we actually have a field from atoms, and if there is displacement, and usually there is oscillation of atoms, that's why we have also introduced phonons, because atom oscillate around the averaged its position. But the potential also like oscillates a little bit because atom oscillates, which shines this potential to electrons. But then like we can expand the exact coordinate of the potential as a series starting from the fixed point position and then gradient of the potential of the just one atom potential. then these displacements which happen because of oscillations can be expressed in terms of phonon operators, because maybe that's the typical harmonic oscillator, and it always works for the oscillator. Of course, there should be a good derivation of this expression, which is not here. They just reference another chapter which I have just shown you recently. And yeah, maybe it's better just to believe that if you think more about this displacement, then somehow you can decompose it into Fourier modes. I mean, obviously you can decompose into Fourier modes and then do this strange but very well-known thing that you relabel the displacement field. I mean, the modes which you get from decomposition to Fourier mode to operators, and that's how you get the second quantized operators. Well, who knows, quantum field theory will maybe even write this immediately. But it's actually a very important formula, because like if you want to get some physical predictions about the material, you need to insert this property somewhere, and that's exactly the point where you should insert the particular properties of some material. And this formula doesn't tell you, unfortunately, how exactly you should insert some physical properties. There is the mass of atoms, but what if you have several mass of atoms? What if you have several frequency of phonons that is there, not only one frequency of phonons? And a lot of actually things should be done about this careful introduction of phonons. That's why I was trying to write it here in the main note. Typical phonons. There are a lot of things happens in phonons, and right now we are just using this theory. Yeah, some experiments, some this type of theory, and the goal is to tell how exactly we should add this formula. Should we have two? What if we have a different primitive cell, so on? So that's the formula that we are advised to take based on Alexandrov and Mott's book. And right now I don't have a clear derivation from somewhere here, that formula. We can see that a lot of similar things are written in Bruce and Fleischberg book, for example. And then some people like to calculate heat capacity and many other things, but when you really try to understand why these formulas appear, then everything becomes very not obvious. And I haven't reached this level of understanding to derive you exactly this formula with this constant. I just understand that this is the vector of polarization, this is the mode, and this is the wave, like typical Fourier decomposition. And okay, we plug this displacement to the real potential in the series expansion, and then we have this term here because that's the potential that acts on electrons, and this term also acts on electrons. And that's how we have this second term, because this is the static field of just atoms, and this is the one that corresponds purely to oscillations. That's how we get this term of electron-phonon coupling, where there is this gamma, which is a famous gamma, the constant of electron-phonon interactions. It's also really actually a good question, like what is the value of this constant? because of Gorkov-Zelensky writes, as far as I remember, just the constant, and Levitov-Shitov also write. They write only the constant. Here we have this constant as a function of momentum, and we have different frequencies of phonons. So maybe this formula is more general. However, also I haven't seen yet that exactly this formula was used in some experiments. But okay, at least we can remember that there is such gamma, and after introduction of such gamma, we introduce also another constant, which is effective gamma, let's say. Like somehow only longitudinal plasmons, longitudinal maybe phonons, that's what it means, are more stronger than others. So the simplified version of this Hamiltonian is this Hamiltonian, where we have an effective constant, which is V, and not just gamma. Okay, that's the model. Like, then right now there is a question how to get some physics from it. And the well-known approach is to say that, okay, we are working with weak coupled electrons and phonons. That's why this term is weaker than other kinetic terms. That's why we can just use a perturbation theory, because that's what we were told from quantum mechanics, that if some term is way less in value than other terms, then we can use it as a just perturbation. And that's why we set the ansatz as a plane wave and use the perturbation theory, which is the typical one from quantum mechanics. And again, some peculiar mathematics appears, which is not very complicated, but still there is a lot of sense to just skip this mathematics and get the value of the energy that we have. The exact value of energy for slow motion is written like this. And the term that corresponds to a kinetic part has some effective mass, which is claimed to be this formula. Okay, and that's the main thing here. There are also important statements about the value of gamma. I was discussing actually several times these values of gamma, why this value is so. And if you use the formula here, like for phonons, for, as it's written here, optical phonons, where omega is proportional to q, to this one to q, or this one to q, then you can see that one q cancels another q, and you get a square root of q. So something is clearly wrong here, or I mean acoustic. If you use acoustic ones, then you get the square root of q, so it works. But for optical and molecular, it doesn't work, and I don't have yet right now a derivation of these statements. But soon we will meet molecular phonons, and this is the third out of 3 Holstein model, which I planned to discuss today. And it's not obvious how to get this value of gamma from optical modes. I had some discussions, but it didn't help me. They didn't help me to understand it, so let's just keep it. There is a complicated thing here, because of which that formula is not applicable for optical phonons. It's not clear why, but that's the case. And for molecular crystals are some special crystals for which this model is not applicable. I mean, yeah, it's applicable, but you need to get the value of gamma, which you can't get in any like reasonable way. And that's why there are still left questions about it, but that's how it works. Okay, the next part of the Fröhlich Hamiltonian that I wanted to tell you, it's not about this and this relatively useless ideas, but about the next value of alpha. So for this value of alpha, the perturbation theory does not work, but luckily in 1953 there was a work which told us how we should work in this case. And it's presented here. So we are told to do two transformations. The first one is here, that we need to rotate in a clever way the Hamiltonian. There are some mathematical features of it, and after the first rotation we get this model where we have no electron coordinate. What is this gradient? If it was acting on electrons, it's not right now for me clear actually. But that's the claim, that there is no electron coordinate, and that's actually true. We have the operators, which are the operators for phonons, and VQ are just constants. So the idea is that after some transformations you can get a simplified Hamiltonian where the perturbation theory is applicable, and that's what happens here. You see, it's not easy to explain what's going on here. So let's not focus on these statements that I don't fully understand. I understand that this is the simplified version of the Hamiltonian, and to get it we need to do these rotations. Then we put the substitution for phonons and electrons. So we fix electrons with some particular momentum. And right now here definitely there are no operators which act on electrons. We have only phonon operators and constants. And here we do the second transformation. We use another function, like the same exponents, but now with this function, where we don't know little f. But later we can find some condition on little f. And here we see the energy that is obtained from the this transformation with unknown f. So it's a complicated equation which has no d operators, because this particular property of the s function, I mean it's also operator, s operator under the log exponent. It's also a good idea to rederive it, but right now the idea is to just grasp main feature. And this equation is not really giving us much because we don't know this f, but we can maybe use a variation method, which is similar to the saying that we need to take functional derivative. But I guess by variational method we get the value of f as some unknown parameter eta, and then we Yeah, like the problem here is that we have some mathematics that is not taught in typical course of theoretical physics. That like what to do with this equation. It's a very complicated equation. Um, mm, like we don't know f. We have some over things that we don't understand, like q. How many values does q have? Maybe it has one value, as we typically hope, because we don't want to work with several modes of phonons. But if we have a several modes, like how many of them, we like also don't know. It's a rather abstract equation. And like, okay, we use something that is called functional derivative, and then we are using maybe the minimization. Okay, if you want to get some more explanations, okay, maybe I don't have in this uh, note, and I don't want to open other projects, but there is a book by Indian professor of Polarons who did some derivations, but also I mean I think in several other books I saw this derivation. It's a famous derivation, and the idea of it is that if you really understand this formula, then using some very not typical mathematics, you get the value of eta. And you also get the value of f, which has this value of eta. And then you just expand that formula as it's shown here as a function of alpha. And alpha, like where does alpha appear? Okay, and you will get, I guess, some constants here and here, which should combine to alpha, and that's how you get this formula for mass enhancement. You can be very surprised because the method here is absolutely different. We haven't used anything what was before. I mean, remember, like comparing everything what happened here and the thing that happened here is just a perturbation theory. Okay, later we also had a perturbation theory, so there are some similar things, but we use two transformations. We basically, yeah, maybe it's not even at all a perturbation theory, it's just a second rotation where we use this formula for rotations. But the result is the same as a perturbation theory. And currently it's still not written in textbooks why perturbation theory gives you the same result as this rotation. I'm not sure it's known in science or not. At least I don't understand this. But that's the famous statement that using two rotations, you get this formula for the mass enhancement. And we clearly see that it's enhancement because 1 plus something. And that's the same formula as was before. Okay, finally we are reaching the third of the three point in my to-do list to tell you. And the third most famous model about polarons, which is called Holstein model. And we also had already a preview of this model when I was telling you that for some reason that gamma that was in the electron phone interactions here and exactly here in the full Hamiltonian that connects electrons and phonons. Yeah, it's better to point on this formula that select phone interactions. So we have gamma here. So for some reason this formula is not working for molecular crystals, and a lot of complicated questions appear, but if we don't want to answer them, we can just say that, okay, for molecular crystals, there is the Holstein model. And right now, this is the last point of my stream today to tell you what is known about Holstein model. It's better for me not to comment any motivation about Holstein model, because there are just complicated statements. There is a connection of ground state energy and the constant of electron-phone interaction. There is another expression of ground state energy. There are some references. Let's just try to understand the construction of Holstein model to understand at least why this model appears as it appears. So the idea is that we again have electrons, phonons, but we imagine the situation that there are two sides and electron travels from one to another. Then for this case, for phonons, we can use the model of harmonic oscillator. For electrons, we can use this Hamiltonian, which tells us that there is a kinetic term and there is potential because of these two atoms and these two atoms. This is the potential energy. And each potential energy has two potentials of both atoms. By the way, it's really interesting point where we can think about that, like if we want to do a good science, right, we can like use some advanced Green's function method, or we can sit and write some relatively easy model like this one. It looks relatively easy, but it asks so many questions which is maybe impossible to answer using the whole Green's function formalism. So maybe sometimes we don't need to have some advanced theory, we need to have some good idea and some particular method for particularly this theory. And right now that's the best example for what I'm saying, because later we'll see that there are some results which are very not obvious and very unique, which are not driven in other models. And we claim that this model is applicable for molecular crystals. There is no explanation what do we mean by molecular crystals. Of course, based on this model, we mean that these crystals can be described by these two atoms. But why we can't describe these crystals with Landau-Pekar model, the first one, or Fröhlich, the second model? I mean, we can describe it with Fröhlich model, but we need to find the proper value of gamma, and there is no way to find that gamma is a constant using just that theory. So finally, we can't still derive this model from the Fröhlich model. I mean, at least I right now don't understand how to do it, and I think it's impossible to understand it in like some months of work on polarons. But okay, we have phonons, oscillations of these atoms. We have electron that travels from one pair of atom to another, and we have, of course, electron-phonon interaction, which is a funny formula. It's very easy and unusual, however, it's very natural, right? We have like, what is energy? It's force times displacement. So if electron is displaced, then there is a force which is calculated just by the derivative of potential. Yeah, and I had once a discussion why there is 1/2 here. Really, I don't remember right now. There is an option that's from the Taylor series, and there is an option that's because the sums more than we need, so we need to divide by half to get the sum that we really need. Maybe the first one is the better explanation, and we also have this minus here, which also should be explained somehow. Yeah, right now I forgot this explanation. I remember that once when I had a discussion, I was told that yes, that's the correct formula, and I was given a reason, but I just forgot this. And okay, that's our model. These three Hamiltonians together. Again, it's a good point where you can plug it to ChatGPT or to give it to your friend mathematician to ask him to get some like ground state energy, for example, using this model. I'm not sure what would happen, but I know what is written here in this book. And we are told to act with this ansatz. So we say that our system is totally described by this wave function, where we have electron yeah. So that's how it works. I remember that we have two wave functions like omega. Omega is here. I mean W is here and W is here. And yeah, it's written here. The total wave function is a linear superposition. So electron can be or here or here. All these positions are can be we can get them from with different probabilities. But also we don't know in which pair of atom it's more probable to be. So we also have these coefficients that tell us how more probable is to be here than here. And since we're doing this purely quantum mechanics, we are writing Schrödinger equation. So for each W, there should be this equation satisfied, which also like really makes sense. And right now, if we how to get this equation, by the way, I really forgot. So it's written that we need to use Schrödinger equation for the total wave function, and that's how we get these two equations where we redefine gamma. I mean, where is gamma? Gamma is here, and also J. We redefine J because we didn't have yet any gamma and J. So that's the place where we introduce them, and the Schrödinger equation becomes two equations. So let's see what happens here. Of course, that's the eigenvalue. So we have a stationary Schrödinger equation. That's the phonon part. That's the electron part. So they're similar in both places. This is the electron-phonon interaction because that's exactly that force that I have just discussed. It's in both places, and we also have right hand side which has like overlap integral. Since no one here in the chat and will help me to explain why do we have this right hand side, because I don't see how we can get this W star W, and there is a V, so maybe V of R can hint us. Okay, maybe V is somewhere here. See, like that's the problem that I haven't been deriving this by my own hand, so I don't clearly see how this thing appear here at the right side, but V can come only here or from electronic side. Maybe from electronic side, maybe from here. No, that's okay. There are two options, or from here or from there. I don't see how both options can be realized, so at this point I'm just claiming that that's the outcome. I can't explain you how J appeared here, with two W's. And that's like the first step of Holstein model. That's the Holstein model, that Hamiltonian full one, and this is the total equation that we have. And in that model, this model that I'm just telling you, there are several sub-regimes, for example, adiabatic and non-adiabatic regime. And let's just look at the results, because it's already a lot of time has already passed. So I will just tell you what are the results, and they can be obtained by proper substitutions, and then some also not obvious mathematics. And that's the formula that we have for the eigenvalues. We have some EP, which is now a different one, not the previous one. It's for Holstein model. And that's their eigenvalue. Omega is the frequency of electron that should travel, or no, it's a frequency of the phonon fields. No, no, that's the wave function, so that's just a coefficient. So coefficient oscillates, that's how maybe it should be. That electron can be on the left or on the right, and then only one coefficient is not zero. Then so maybe omega is a constant which is related to the phonons still, because omega is, as far as I remember, often related only to phonons. So maybe we need to know that these coefficients oscillate like phonons do. And I just want to explain a little bit this formula, because that's the main result of the Holstein model. And the energy, there are two eigenvalues, and this is the second eigenvalue, that we have like some constant, then some energy which is also dependent on that constant omega, and then we have also some splitting by some value of this type, which also don't know. So that's the disadvantage of this model, at least in this form how it's written, that we don't have at all any physical prediction, just some formulas left here. But Holstein model is a famous model, so definitely there are some physical predictions, they're just not written here. Okay, then the second out of two limit is the adiabatic polaron, where we have a different ansatz for the coefficients A for different limit, and that's actually two variables that set our limit, the J and omega. So J is comes from the interaction of electrons, so this is a wave function, this is purely from atoms, and omega is the external, I guess, frequency of oscillations. So we just need to believe that if we use this ansatz and plug to Schrödinger equation, then we get eigenvalue of this form. And I'm not sure what we need to do next, because if we have eigenvalue, eigenenergy, then it's already fine, but maybe we need to find the wave function. That's why we still work with Schrödinger equation. Yeah, okay. So we are claimed that if we use, okay, it doesn't matter what, but if we use semi-classical approximation for this Schrödinger equation, then we get this shift of energy. This site Landau-Lifshitz, I guess it's quantum mechanics. And they also give analogy to this potential well of this effective potential, which is obtained from substitution of this eigenenergy. I just wanted to understand what are we really obtaining finally, and I guess we are obtaining this one formula for the split of energy. That's what Holstein was doing, and he was after it famous because of this model. Right now it's nearly impossible to understand what is the really physical value, because we don't see the effective mass which we got from previous predictions. We have just change of energy with some lambda, which comes from I don't know even from where, because we didn't have any lambda before. This lambda is already here. Let's try at least to understand where lambda comes into the game. If you think that this theory is bad, then don't blame me. It's written by Alexandrov and Mott, and I just tried to understand it. Yeah, you see, look, the problem with this discussion is that there is even no lambda at all. Lambda appears here. Okay, there is no way how to get it, but using my great application, I can at least try to find the old paper, old fundamental theories. Yeah, and right now, just in a few clicks, I'm getting the original paper by Holstein. Is it a good idea? No, because it's better to be focused on little model and just claim with like assuredness in my voice that that's how it works, but it sounds like a bad idea. So I mean, I just don't like to do it. I like to really be fair if I understand something or not. And in ideal situation, this original paper would really help us to find out what is this lambda. But in reality, this original paper has a different notation. So, and slightly different. You see that Alexandrov and Mott didn't lie us. That's exactly the model that we have dealt recently with. But like if we right now want to get the lambda, it's still not obvious. Actually, I have some buttons, like connection buttons, that should draw a connection between this article and that article. But of course, they don't work because we don't have a budget for any AI development. We also don't have a budget for development of this application. It's developed approximately fully by me, and I'm more expert in Polarons than in programming. That's why I just wanted to show you that it's a really bad idea to find something in old articles, because like right now I can't find it. Like, where is this formula? Introduction of Lagrange multiplier. Okay, fortunately I jumped to the wrong part. So I can't tell you anything about this lambda. I don't know where this lambda appear, but yeah, maybe this thing can help me. Yeah, like it's still a very valid question, where does lambda appear? But okay, maybe we can ask the question about the minimum, get the formula for the minimum coordinate, and that's how we can find out what is lambda. Another thing is that somewhere there in Alexandrov and Mott's book, it was stated that this is the value of the lambda. There are several values, several formulas for it actually. It's not obvious why they are the same, but it's also maybe sometimes known as constant of electron-phone interaction. Not that alpha, but also lambda. And then another question appears, like, well, why, how this alpha is connected to lambda. Yeah, these are complicated questions. I'm not sure, but if you ask me, maybe I will answer you like this, that that's the value of lambda that sits here. Maybe if you transform this thing, you can get this equation where here you have a square of this term. And h bar is maybe set to unity. I don't know how to explain this another way. Okay, but somehow you get some minimum, then you get the change of energy. Maybe it's also a polaronic shift, what is called. But that's how it works. And we don't have any physical predictions right now from this model. But that's already a good time to finish the stream. So in a nutshell, there are a lot of things that happen in the theory of polarons. I just give you a little introduction where I jump through main results. Main results of basic models. There are no physical predictions of these models, but later some people might say, look, there are multi-polaron problems, and there will be very complicated mathematics about multi-polarons, which is very far away from all what I have discussed here, but still common sense tells me that the basics of polarons is here. Then there is a very strange and already dead theory about bipolarons. Well, yeah, like there are different opinions about bipolarons. Alexandrov and Mott were sure that they are the best ones for describing condensed matter and high temperature superconductivity. However, it was impossible, at least for me, after several months, it's still impossible to use theory that was developed by Alexandrov about bipolarons. And I think that's the main reason why bipolaronic theory is really dead. And some people say that they do not really predict what it should predict, or what is like also known in physics. And then after this theory in scope of polarons, really a lot of things happen, like bipolaronic liquid, charged Bose gas, some experimental ideas, mid-infrared conductivity. And see, I don't need to scroll, that's the great thing. I need to just click, and approximately I'm on the right page. If I had some money for development, I would develop application and claim that I'm exactly on the right page. Okay, the mid-infrared conductivity is actually somewhere a little bit above. Where is it? Evidence for small. I'm already here. Yeah, but I just wanted to show you that yeah, there are a lot of plots with peaks, some photo effects, resistivity, because electrons, if they are polarons, they take part in resistivity. That's actually the famous, I mean, not very famous, but a plot which is known in my institute, and I discussed this paper once with authors of this paper. That there are some peaks, then, like how many years have passed, maybe 60 or 40, and still no one can yet explain some not consistency of theory and experiment. And here and here and here, also a little bit here, so people just forget questions that they can not answer because they don't have this nice digital approach of notes where you fix your questions and then you can return to your questions and not to the theory that pretends that there are no questions. But a lot of experimental consequences are there, a lot of advanced, special, forgotten by everyone theories are there about somewhere here Fermi liquid phase transitions of the polaronic Fermi liquid. That's only from Alexandrov and Mott's book. It's a very big and dense book. Then there are some other calculations by de Vresi, yeah. A lot of things was done by Pekar. It's also actually forgotten and dead. There is an approach from supercells which uses DFT, where they start with something which is similar to our Landau-Pekar model. And that's the motivation to listen again at the beginning of this stream, because they also start with similar model, but in different Kohn-Sham formalism. I still haven't understood their special approach, but they claim that they have some very physical prediction using their very advanced numeric codes. That's what they show us. Some spectra and some beautiful image of localized electron because of polaronic effects, I guess. And I am not expert of what's going on in their article, but this article looks very advanced. And there is a second article, by the way, by the similar authors. And again, I mean, here you can see explicitly the first model that I discussed. A little bit different notation, but still it's very, very close to the one that I discussed. And you see even here the value 16 divided by 5, which I showed you recently. But then they use again DFT, so to understand it you would need to understand DFT, and it looks like a pit hole, but if they have some predictions, that it means that it's a good theory to focus on. Okay, as I said, there are a lot of experimental consequences. There are, what else to tell you? A lot of special effects, which is better even not to mention. Some people are still, I mean, they're not using, but once I had discussion with Viktor Kabanov, some of these models. So theory of Alexandrov and Mott is not really dead, it's approximately dead, but not really, because sometimes something here appears in some discussions, at least in my life. And there are a lot of actually predictions. They predicted that there are no strings, however, if you really want, you can find a place where there is something that looks like a string of polarons. But at least it gives us the historical perspective. We understand what is really done in science, what people were doing for the last, I don't know, 60 years. And polaronic field is a very big field. There are a lot of, how to say it? Oh, that's also a famous, by the way, article. A lot of theories written, a lot of experiments are done, but no one has ever tried to write a consistent theory that fairly says that something is working and something is not working. It's purely like undiscovered field, at least it feels right now for me. because different people use different methods. Currently I have not covered even like 1% of all methods that I used. I just told you one of the several really famous models. And if you want to try to get some experimental predictions, like for example what is done here about optical conductivity, it's really impossible. It's really very hard to do. You need to learn some specific theory that goes way far from the theories that we have covered. And I even haven't told you some things about like Green's function method, screening. What else? Okay, we can maybe even derive superconductivity from that Fröhlich model, but it's maybe rather philosophical statement than the physical. Okay, so that's the introduction to Polarons. I hope you liked it. Yeah, and also I hope you got interested in this application. So if you want to contribute to development or become a user, you can use our webpage to leave some comments, to join waitlist, for example, or to subscribe to this channel. So thank you very much for your attention, and bye bye.